Hi, this is Jonathan Gardner. We're now in Chapter 8 of 10 chapters, I believe. Double checking. Yes, 10 chapters of Griffith's Introduction to Electrodynamics. I'm working from the second edition. You probably have the third edition. The fourth edition is coming out soon. So, a bit of a history. We've covered electrostatics. We've covered the potential, the electric potential V. We've covered how electrostatics works in matter. That's where we discovered the susceptibility and permittivity and things like that. Then we went to study magnetostatics, and we discussed how magnetostatics works in matter, and then we combined them all together into Maxwell's equations in the last chapter, in chapter 7, where we discussed electrodynamics. And in the electrodynamics chapter, we covered very briefly some of the most important topics that govern all the rest of the things we're going to cover. Among them is we covered how energy works. We covered the Poynting vector, E cross B. We covered the Maxwell stress tensor, which hopefully isn't too difficult to conceive of anymore now that you've had some practice with it in the problems. So now we're going to cover a corner case of electrodynamics where we see electromagnetic wave. So this section, section 8.11, serves as an introduction to where the wave equation comes from and how it applies to real life in electrostatics and magnetostatics. So Maxwell's equations, in a region of space where there's no matter and there's no charge, we have the divergence of E is equal to 0. That's Gauss's law. We have the divergence of B is equal to 0. That's just common sense because we don't have any magnetic charge. Trying a different black marker. And we have the curl of E. Oh, much better. That's equal to negative the time derivative of the magnetic field. And the curl of B, remember we're dealing in regions of space where there's no current. We have mu naught, epsilon naught, and the time derivative of the E vector. Okay, so then if we take the curl of these two equations, we get something interesting. So let's do the curl of E. So the curl of E vector is going to be equal to the curl of this negative time derivative of the magnetic field. Well, the curl of the curl, if you look in the front cover, if you open up and remember multivariable calculus and what the curl of a curl is, this is just the gradient of the divergence of E, which is going to end up being 0 because we're not dealing with any charge, minus the Laplacian of the E vector. Okay, so that's the Laplacian of the x component in the I hat direction, Laplacian of the y hat in the j direction, the Laplacian of the z component in the k hat direction. And if we take our curl to the inside, we get negative the time derivative of the curl of b. Well, the curl of b is just mu naught epsilon naught, so we get mu naught epsilon naught, and the time derivative of E vector. And I think I lost a minus sign somewhere. Yes, I lost a minus sign. Okay. Now this is 0. This is negative. That's negative. So we end up with the Laplacian of E is equal to mu naught epsilon naught, the second derivative with respect to time of the E field. So we have here an equation that depends only on the E vector, but it's a second derivative with respect to time and second derivatives with respect to the various coordinates that you're using. For the B vector, we can do the same thing. So we take the curl of this equation. So curl up. The curl of B is equal to mu naught epsilon naught. The time derivative of the curl of E, I'll just write that out. The curl of the time derivative of E. Okay. Once again, the curl of a curl is the gradient of the divergence minus the Laplacian of the vector. And then we have mu naught epsilon naught And the time derivative of the curl of E, well, the curl of E is the negative the curl of B, so negative the second derivative with respect to time of the B field. Okay? And then once again, there's no magnetic charge, so we get the Laplacian of the B field is equal to mu naught epsilon naught, the time derivative, second time derivative with respect to time of B. Okay, so we get a extraordinarily similarly looking equation for B. And the pattern for second derivative, the pattern is that you have the Laplacian squared of some vector field is equal to 1 over v squared of the second time derivative of the same field. Okay, and that is the basic equation for a wave equation. This is the classical wave equation. Okay, v is the velocity of the wave, that's how quickly it travels. And in our case, we get a v, rv is equal to 1 over the square root of mu naught epsilon naught. And if you plug in the epsilon naught that you measured when you calculated Coulomb's law from reality, and you plug in mu naught that you calculated when you uncovered, I'm going to get this wrong, the Biot-Savart law from reality, okay, then you find that these multiply together to equal 3.00 times 10 to the 8th meters per second. Okay, and I know for the modern physics audience, you've probably been told since you're a little baby that light is just electromagnetic fields waving through space. Well, to Maxwell, who saw this result, this was very surprising. Why would the coefficient for Coulomb's equation and the coefficient for the Biot-Savart law be apparent in the speed of light? Why would those two things match? And when you really think about the fact that when you have a static electric field attracting charges, repelling charges, and you have a static magnetic field, constant currents attracting and repelling other currents, that is fundamentally and intrinsically related to the speed of light. This is one of those things that give us great hope that there's some grand unification theory just waiting around the corner, where all the constants of the universe that we discover are really all related to each other. Probably just different facets of this one constant that defines everything. So this is one of those beautiful results. For inside matter, I'll do this rather quickly. You have your Maxwell's equations that look like the D field is equal to 0 because there's no free charge, and you have your B field equals to 0, and you have the cross of your E field, or the curl of your E field is equal to just negative of the B field, the time derivative of the B field, and you have the curl of the H field, okay, is equal to just the time derivative of the D field. Okay, where did all those funky constants go? The answer is that they are absorbed in the D field and the H field themselves. Okay, so if you have a linear medium, then you can relate the D to your E field with the proportional constant epsilon. And if you have your H, by the same token, is just 1 over mu, the magnetic permeability of the material, to the B field. So now we can plug in these for the D and B, the D and the H. And you can reduce these equations to, this one becomes the divergence of E is equal to 0 because E is proportional to D. Divergence of B is 0, stays the same. This stays the same, that stays the same. So the H becomes 1 over mu B, right? So let's put that in. So we have the curl of the B field is equal to, we have a mu, and the D field is epsilon E field, so we have Okay, so basically we get the same equations that we had before, except for now we have the velocity is equal to 1 over mu epsilon. Okay, and this interesting, curious result leads us to conclude that the speed of light is slower in linear media, linear and homogeneous media. That means that it doesn't change its mu or epsilon as you move to different parts of the material. So in linear media, the speed of light is substantially slower. In fact, the speed of light is equal to the speed of light in free space divided by some proportional constant n, which is the index of refraction. Okay, so if you go back and study Snell's law and that physics that they were doing back at the time that Newton discovered the 3 laws that govern all matter, now we can calculate, just based on the magnetic and electric properties of the material, what n is supposed to be. Epsilon naught over mu naught. That's n. And this is a rather curious result. This is basically the nail in the coffin of the fact that light waves are really electromagnetic waves. There's no substantial difference whatsoever, and there's no reason to think of them as being any different than that. Now, for what reason does light landing on a prism break out into a spectrum? Well, the answer is rather simple. Depending on how fast the wave is shaking, the epsilon changes for different materials. There's a response based on if you're moving back and forth rather quickly versus slightly slower, the epsilon is different, so they get different speeds, and so the index of refraction for different wavelengths of light is different. So anyway, so these are the foundation for everything that you're going to be doing for the next couple sections. You don't have, this is an easy enough derivation, you don't have to memorize it. The one tricky bit is remembering the curl of the curl as the gradient of the divergence minus the Laplacian. And other than that, it's very easy to derive these equations even for linear media, just using things that you already know. So I hope you have fun, as much fun as I did studying this chapter when I was in physics. The last chapter was by far the most difficult, I think, of the entire course. And where I really understood chapter 7 was halfway through chapter 8. That's really everything came together. So hope you have fun. If you have any comments or suggestions, you can put them in the comments below or make a video response. Don't be shy. And if you be sure to like and subscribe to my channel so you can get updates when they come out. Thanks for your time. Bye-bye.